Hello, and welcome to Talk and Full Blood Count. Because it's quite a big talk, I'm just going to do the red cell bits in this particular talk. Because I come from a town with a daft accent, I'm going to put some subtitles in. So to understand what's going on, diagrams and bits of explanation will go in this blue bit here, while what I've said will go in the red bit. Now, only the important bits will go in the red bit. If I'm waffling about something, that won't be in the red bit. Any writing that's important will be in red. Any stuff that's in black will be jokes, because I have the attention span of an emergency physician and I need to do jokes just to amuse myself sometimes. So to start, we'll look at normal haemoglobin levels. Now, these are UK values. We'll come back to why I'm telling you this later. And normal values in women, this is 11.5 to 16.5, and in men, it's 13 to 18. Now, don't think you should memorize this, but over time, you'll just get used to what's high and what's low. On that, when my wife was anemic, my daughter, who was 7 at the time, asked what normal values were, and I told her, and she told me that the low haemoglobin for women was sexist and I needed to sort it out. Now, the other thing worth noting is these results are in grams per decilitre, so sometimes we get values from labs outside of Lanarkshire. What you need to know is that there are 10 decilitres in a litre, or 1 decilitre is 1/10 of a litre. So if you're looking at results from other places, 123 grams per litre is the same as 12.3 grams per decilitre. First, we'll talk about causes of a high haemoglobin because it's easiest. An important and common one is dehydration, where even though your haemoglobin level may actually be normal, dehydration gives you the impression that it's actually high. So if you think about it like this, if you have 10 cells floating in 1 ml of plasma, that will give you a concentration of 10 cells per ml. But if dehydration causes the volume of plasma to decrease by half, down to half a ml, you still got the same 10 cells in half a ml, which is a concentration of 20 cells per milliliter, which is an increased concentration, but the same number of cells. Now, 50% dehydration is going to kill you, unless you're Clint Eastwood or something. But in normal levels of dehydration of 5 to 10%, you will have a haemoglobin that looks artificially high due to lack of plasma, when actually the haemoglobin level is normal. To work this out, we use the hematocrit. We get the hematocrit by spinning blood. What I mean by spinning blood is putting it into a centrifuge and spinning it down until it breaks down into its constituent parts. So that's splitting into red cells, there's a tiny layer of white cells, and then plasma. And the hematocrit is the percentage of this solution that is made up of red cells. Now, normal values for hematocrit is 41 to 50% for men and 36 to 48% for women. But the thing is, some authorities reckon that knowing the hematocrit has no real advantage over knowing the haemoglobin, and these days, rather than measuring the hematocrit, analyzers will calculate it from the various other values it knows, including the haemoglobin. So, and if you plot hematocrit against haemoglobin, you get a pretty much straight line. So I'm not going to say an awful lot more about it. The next cause of a high haemoglobin I want to talk about is chronic hypoxia. So if the body spends a significant time where it just doesn't get enough oxygen, it stimulates the bone marrow to produce more red cells. An interesting example of this is if you move to La Paz in Bolivia, which there's arguments between Wikipedia and other sources as to how high above sea level it is, but certainly it's above 3,000 metres. And average haemoglobin levels there are 13 to 21 for men and 12 to 19 for women, which is a little bit higher than the average in the UK. If you think about more medical causes rather than living at high altitude. These include COPD, heart failure, and particularly important is congenital heart disease, particularly those where there is what's called a right to left shunt. So some of the blood, instead of passing through the lungs, is going straight to the left, from the right side of the heart to the left side of the heart without being oxygenated. All of these cause an increase in haemoglobin levels. Number 3 on my list is excess erythropoietin. So as you'll probably know, red cells are made by the bone marrow, and the kidneys have an influence over this by producing the hormone erythropoietin. Now, erythropoietin release stimulates the bone marrow to produce more red cells. It also reduces red cell distribution, but I didn't know I would draw that. Erythropoietin is normally fairly carefully regulated and would only increase if the body was experiencing chronic low oxygen levels. It's almost like it all fits together. But you can also get excess erythropoietin production in renal carcinoma as the cells overgrow. Certain types of liver cancer produce erythropoietin as well. And erythropoietin can be injected. Frequently that happens in those with kidney disease who aren't producing it normally, but it can also occur in athletes who can't afford the train fare to La Paz. And final cause of raised hemoglobin I'm going to mention is polycythemia rubra vera. Some people call it polycythemia vera, which is a rare myeloproliferative disorder where the bone marrow produces an excess of red cells. So that's pretty much it for the causes of a high hemoglobin. Low hemoglobin is a little bit more complicated, but I'm a fairly simple bloke and I'll try and explain it as simply as I can. So low hemoglobin is called anemia. It is going to get more complicated than this. And we divide the types of anemia up by cell size. So the average red cell is 80 to 100 femtoliters in volume, and a femtoliter is 1/4 of a litre. Now, I'll admit this diagram looks like it's the width of the cell, but I couldn't think of a way to easily show volume. Actual cell widths are about 6 to 8 microns. Anyway, we divide it up by size. So anemia where cells are less than 80 femtoliters we call microcytic. Cells that are normal sized, so 80 to 100 femtoliters, we call a normocytic anemia. And where cells are bigger than 100 femtoliters, we call this a macrocytic anemia. We'll talk about microcytic first. The top cause of microcytic anemia is iron deficiency anemia. Red cells are full of hemoglobin, which is partially made of iron, and from here on in I'm going to use the picture of an iron to represent an iron. It's a kind of jocular shorthand, an ionic iron, if you will. So when there's a lack of iron, we have a smaller red cell. So some of you might have noticed I've skipped ahead a bit, which I'm going to pretend was planned. I've been talking about the average volume of a cell, but where do we find it on the full blood count? Well, another word for average is mean, and the red cell goes by many names. One of which is the red corpuscle. So average size of a cell can be called the mean corpuscular volume, or MCV, and I'm going to use it MCV from here on in when I'm talking about cell volumes. So when we're talking about iron deficiency anemia, we first need a low hemoglobin, a low MCV, or small cells, and lastly we measure a protein called ferritin. If ferritin is low, we can safely assume iron deficiency anemia. But ferritin is also what we call an acute phase protein. That means it goes up when we're ill. More specifically, ferritin is a protein that picks up free iron in the blood. And this is important because, say, when we have an infection, the bacteria that are in our body need, or viruses, need iron to divide and grow. And what ferritin does is zips around, hoovering up all this iron so that the bacteria don't have iron to divide and grow. Or if you've had an accident or surgery and there's been a lot of cellular damage, then again there's a fair amount of free flowing iron, and ferritin increases to try and absorb that. So whilst low ferritin is a reasonable mark of iron deficiency anemia, if the patient is sick, they may have low iron stores but a high ferritin level. The point of all that was, if ferritin is high or normal, we have to think of another test. And that test is the total iron binding capacity, or TIBC. To test TIBC, we take the patient's blood and we add iron to it, and we see how much iron the blood can bind. Total iron binding capacity. But it's actually a proxy measure for transferrin. Transferrin is another protein that binds iron. I'm not going to try it because it looks like someone fired a party popper at your face. But measuring TIBC is cheaper than measuring transferrin. You can calculate transferrin levels from TIBC, but I'm not going to tell you how because I've never had to do it, so I don't see the point. In iron deficiency anemia, transferrin, and therefore TIBC, is high in an attempt to best utilise what little iron is available. Now, some of you might be going, hang on, isn't that the opposite of ferrin, which you said did the same thing? Well, no. Transferrin carries less than 0.1% of the body's iron. It's about 4 milligrams. But it allows iron to be used really easily, so it carries it from one place to the other, so it can be utilised. And actually, it picks up and releases about 25 milligrams of iron every 24 hours, what's called a high turnover. Ferritin, on the other hand, binds iron and takes it into the cells for storage. So if you think of it as transferrin is for transferring iron, so it can be used, whereas ferritin is for ferreting out spare iron and then squirreling it away. Now, that's an oversimplification, possibly even a lie, but it's a good way of remembering it. Anyway, iron deficiency anemia is characterised by low ferritin, usually, and high total iron binding capacity. So that's iron deficiency anemia. The next cause is anemia of chronic disease, or ACD. The good news is that we've done most of the spade work whilst talking about iron deficiency anemia, because the results are the opposite way around. Well, MCV's low, HB's low, but ferritin and total iron binding capacity are the other way around to iron deficiency anemia. So ferritin is high to keep the iron away from the bacteria that needs to divide, the tumour that needs to grow, whatever the inflammatory process is. Transferrin, and by extension TIBC, is low because we're keeping the easily utilisable iron away from the inflammatory process. The other big clue you can get for AOCD is asking the patient if they have any sort of chronic disease. And that's pretty much it for anemia of chronic disease, except we'll come back to it in a bit. Number 3 on the list is thalassemia. The only thing people really remember about thalassemia is that it comes from the Greek word thalassa, meaning the sea, and that's because it was first classified in people who lived around the Mediterranean Sea. Though in our modern, less Eurocentric world, it's important to know it's much more widespread than that. Number 4 on our list is sideroblastic anemia, which is a condition where iron is poorly incorporated in haemoglobin and instead ends up in the mitochondria of red cell precursors, forming ring sideroblasts, which have a ring of iron-laden mitochondria around the edges. Now, I've covered 3 and 4 pretty quickly there, because really you only need to know they exist. Because if your microcytic anemia isn't 1 or 2, then you're going to be asking your friendly neighbourhood haematology lab for help and probably looking at a textbook. The second group of anemias I'm going to talk about is the macrocytic anemias, so that's the ones with an MCV greater than 100. The first cause is B12 deficiency. The second cause is folate deficiency, and I'm going to lump them together because everyone else does, so much so that they are known collectively as the megaloblastic anemias. And I hope in the next couple of minutes we'll all understand why. So to do this, I'm going to remind you of a couple of red cell facts. Firstly, red cells don't have any DNA, so they don't have a nucleus like other cells. I remember being told this was to fit in as much haemoglobin as possible. I don't know if it's true, but it's a nice idea. Only immature red cells have DNA. Also, immature cells are all called something blasts. So red cells are called erythroblasts or sometimes normoblasts. The other fact is, if you cut a red cell in half and look at it in profile, it has the shape of a biconcave disc, kind of like a ring with a thin membrane in the middle of it, or a rolled up condom like you might use to put on an ultrasound probe. This makes it pliable, or to use the technical term, squishy, so it can fit through narrow capillaries. Why am I telling you this? Mainly because drawing this bit made me laugh, but also to understand the megaloblastic anemias, we'd have to look at how red cells grow in the bone marrow. So I'm going to draw erythroblasts to look like a red cell with a nucleus. They don't look entirely like this, but it doesn't matter enough to do it properly. For any cell to divide, you need to be able to make enough DNA for two cells. Once this happens, the cells divide and you get two smaller, almost identical cells. These then grow until they're big enough to divide again. So the cycle continues with dividing and growing, dividing and growing. But you need B12 and folate to make DNA. So if you're B12 and or folate deficient, the growth phase between divisions becomes longer, and so you get bigger blasts and eventually bigger red cells. These bigger blasts are called megaloblasts because megablasts would be too cool. Also, because of the problem with DNA production, some of the eventual cells end up deformed or just a bit rubbish. Anemia arises because the production of cells is slower, and a lot of the cells, the bigger ones and the rubbish ones, are either trapped in the bone marrow or removed from the circulation by the liver and spleen and that. The next cause of macrocytic anemia is reticulocytosis. Reticulocytes are another immature cell type. They're not as immature as an erythroblast, they don't have any DNA, but they're less mature than a red cell. They have some residual RNA in the cells. They're also a bit bigger than red cells, so they need to be in relatively large numbers to cause a rise in MCV. Reticulocytes are released in large numbers as a response to sudden blood loss. The marrow releases a large number of cells a few divisions early to give a temporary boost to haemoglobin levels, with a slight increase in MCV. The reticulocytes mature in the circulation, becoming red cells over a few days. So if you think of reticulocytes like the final year nursing and medical students during the pandemic, initially not quite ready for the job, but in a very short time indistinguishable from the fully ready staff they came to support. If you have an anemia that you're struggling to explain, it'd be worth asking for a reticulocyte count. If it's raised, it can give a hint that there's been a sudden drop in haemoglobin recently. So a recent bleed or hemolysis or vampire attack or whatever. The next cause of macrocytic anemia, well, the next causes of macrocytic anemia I've grouped together because they're complicated. Each can work by a number of mechanisms and can produce a number of cell sizes, so I'm going to come back to them nearer the end. So we're finally on to normocytic anemias, so that's the ones with an MCV between 80 and 100. It's nearly over. Of course, you could always just switch this Wibble fest off and go watch something good instead. Anyway, the first cause of a normocytic anemia is acute blood loss. Now, this is pretty easy. You have X number of blood cells floating around your system, you vomit up Y blood cells, you now have X minus Y cells. Unfortunately, it's not that easy to spot in an uncontrolled bleed. For example, the average patient has about 5 litres of blood, or he does if you want to make the maths easy. So if this person's haemoglobin concentration is 160 grams per litre, 5 litres is 800 grams of haemoglobin. If you lose a litre, that litre has 160 grams of haemoglobin in it, leaving 640 grams behind. But it's in 4 litres, so still has a concentration of 160 grams per litre. So if you measure the haemoglobin too early, you can be fooled into thinking that actually the patient is fine and their haemoglobin's okay. But you haven't allowed for haemodilution. Because the body wants that circulating volume back at 5 litres, fluid comes from other spaces within the body to bring that volume back up. As that happens, you become more aware that the haemoglobin is now actually 128 grams per litre. That's 640 divided by 5. The problem is, haemodilution can take days if the body's doing it alone, but minutes to hours if someone clever has spotted the bleeding and started IV fluids. Even then, it takes some pretty complicated maths to work out the haemoglobin. This is why when you have surgery that involves a fair amount of blood loss, they monitor this, measuring the amount in the drains, in the suction bottle, weighing the bloody swabs, to work out exactly how much blood you've lost. So not understanding that haemolytic dilution can take ages potentially puts patients at risk. Understanding it causes smiley faces on emergency physicians, if that's a risk you're willing to take. Cause 2 of anormocytic anemia is uncompensated increase in plasma volume. Again, this is pretty easy. It's the opposite of the dehydration I told you about earlier. If we increase the plasma volume, then the concentration drops. Often this is our fault by adding IV fluids. So in the last patient, if we discussed, if we had a litre of fluid, that dropped the HB from 160 to 128. And again, frequently the body sorts this out over time. Though sometimes the body wants to increase the plasma volume, for example in pregnancy, or sometimes the body lacks the ability to fix it, for example in someone with kidney failure or heart failure, somebody who's missed a dialysis session. Cause 3 is aplastic anemia. This is where the marrow essentially stops producing red cells, or reduces the production of red cells, and this is called hyperplastic anemia rather than aplastic anemia. So the immature red cells and white cells and platelets, which have common stem cells, are damaged and stop reproducing. Things that can cause this are drugs, particularly chemotherapy agents, viruses and autoimmune disorders. Pregnancy can cause an autoimmune response, or a number of other causes, and sometimes we just don't know, so this is idiopathic aplastic anemia. The clue we get for aplastic anemia is drop in all cell counts, red cells, white cells and platelets, rather than just red cells alone. Aplastic anemia is rare and frequently complicated, so if you suspect it, you're going to want to get haematology advice. Cause 4. I've labelled hereditary oddness because there are a number of hereditary conditions that affect either the red cells, red cell walls, haemoglobin, that can lead to anormocytic anemia. So examples would include hereditary spherocytosis, where instead of a biconcave disc, the cells are spherical, elliptocytosis, where the red cells are elliptical rather than round, and there's various haemoglobinopathies that I'm not going to go into massively. These cells are often more fragile and more frequently removed by the spleen, etc. So their life's shorter, so you get the anemia cause of it. And to be honest, that's about as much as I know, because these conditions are usually picked up by haematology, managed by haematology, and rarely involve the rest of us. But there is one important one I want to discuss briefly, and that's sickle cell. In sickle cell anemia, red cells under stress form sickle shapes rather than biconcave discs. These pass through vessels poorly and ultimately end up blocking vessels, causing what's called a vaso-occlusive crisis. This leads to ischemia in limbs or parts of limbs, infarctions of major organs like the spleen or kidney. It can even cause strokes. It causes priapism, and there's a number of other potential complications like aplastic anemia. To be fair, it's a lecture all by itself. There's a lot of causes ranging from big stuff like dehydration, hypoxia and infection and pregnancy to relatively innocuous sounding insults like temperature change, exercise, stress, smoking, alcohol. But what I really want to talk about is the management of it, because it's frequently done badly. They need oxygen and fluids and analgesia. After you've given analgesia, check if it's worked. If not, give more analgesia. Then contact haematology, or if you're lucky enough to have a sickle centre nearby, contact them. And then check if your analgesia is working again. Repeat analgesia checks is key to the treatment of these patients. Have a low threshold for arranging patient-controlled analgesia, and even with a PCA, you want to check that their analgesia is working. Cause 5 is hemolysis. Hemolysis is the destruction of red cells. Sometimes this happens in the plasma directly. Probably more frequently, whatever causes the hemolysis causes problems with the cell walls, causing the cell to deform into something much like a spherocyte that then gets trapped in the spleen. Again, hemolysis has a lot of causes. Bacteria such as staph, strep and enterococci can cause it. Parasites like malaria are famous for causing it. The hereditary conditions, the abnormal cell shapes and haemoglobinopathies that we mentioned in cause 4 are all prone to this happening. It's often the cause of the short lifespan. In pregnancy, the H in HELP syndrome stands for hemolysis. Prosthetic heart valves can cause hemolysis, And hemolysis can be an early sign that the valve is starting to fail. There's even a condition called heel strike hemolysis, which occurs in runners, so the hemolysis occurs in the feet whenever the feet impact on the ground. There are some clues for spotting hemolysis. These include a raised bilirubin. So when red cells die, the haemoglobin breaks down to heme. Heme eventually breaks down to bilirubin, and so if lots of cells are destroyed in a short space of time, you'll get a sudden rise in bilirubin, with, usually, the rest of the LFT staying normal. In autoimmune hemolytic anemia, the clue may come when blood transfusion phone you to say that the sample has shot up a load of unexpected antibodies. But another clue is to look at the full blood count, specifically the mean corpuscular haemoglobin concentration, or MCHC. I've called it mean cell HB concentration in the slide because it's easier, it means the same thing, it's easier to understand. It fits in the line, and my laptop is running out of red pixels. So how we measure haemoglobin concentration is we fire a laser at the blood, put a sensor on the other side, and the sensor measures the light coming out of the blood and calculates the haemoglobin concentration based on how much light is absorbed or refracted or whatever. This is then used to calculate the MCHC. Generally, MCHC follows MCV, so the mean cell volume we mentioned before. So it's normal in a normocytic anemia, low in microcytic anemia, and high in a macrocytic anemia. But there are a number of conditions where MCV is normal, but MCHC is high. Because the shape of the red cells alter the amount of haemoglobin that fit in the cell volume. So spherocytes, which are one of the precursors to hemolysis, give a raised MCHC due to the loss of the disc shape and the cell being all fat and that. Sickle cells do the same thing for slightly different reasons. Lastly, if a lot of cells have burst, then there's haemoglobin floating free in the plasma, which the machine still measures because it doesn't know what's cell and what's not, giving a false high MCHC, which can be a clue to hemolysis. The other thing that can confuse the machine, and it has nothing to do with hemolysis, but I can't be bothered doing it again later, is hypolipidemia. So lipids floating around in the bloodstream can also falsely alter your MCV. The definitive way to diagnose hemolysis is for a hematologist to look at the film down a microscope and find red cell fragments. This isn't necessarily available 24/7, which is why I've mentioned all the other stuff. Once they've found this, hematology then can advise you on things like Coombs test and other dark magic. Cause 6 is anemia of chronic disease again. So while we've mentioned the mechanism of ferritin reducing the amount of available iron to keep iron away from nasties, other mechanisms do exist. So, for example, in patients with kidney disease, you get reduction of erythropoietin production, which then leads to normocytic anemia. Other conditions reduce the marrow response to erythropoietin, causing much the same thing. Red cells may have a reduced lifespan due to hypersplenism, or red cells may be gobbled up by macrophages. So there's lots of stuff for AOCD, and a careful history and examination may help you find the cause of normocytic anemia. Cause 7 is drugs, and now we're well into the causes that give more than one type of anemia. So best known is probably NSAIDs or anticoagulants that cause GI bleeds that lead to a microcytic anemia due to chronic iron loss. But when you stop the NSAIDs and start a PPI, that can lead to malabsorption of iron and cause a microcytic anemia instead. You also need copper to form red cells, and zinc reduces copper absorption. And importantly, there's a massive list of drugs that can cause aplastic anemia. Chemotherapeutic agents and drugs for autoimmune conditions are best known, but antibiotics have been linked to aplastic anemia. But antibiotics have also been linked to hemolytic anemia, as is phenytoin. But phenytoin has been shown to cause megaloblastic anemia as well. So again, it all gets a bit complicated, and I'm really conscious that for the last 20 minutes we've been constantly on the phone to haematology and bothering them all the time. And for this one, it may be worth seeking pharmacist's advice rather than haematology. Cause 8 is thyroid disease. When it comes to the question of why, personally, I've been working for years on the principle that knackered thyroid knackers everything else. But this is supposed to be educational and that, so I thought I'd better find out, and it turns out no one else really knows the definitive answer either. In the underactive thyroid, there seems to be an effect on the absorption of iron, B12, folate, and other stuff required for red cell production. But there was also a study in 2018 suggesting that either T3 or T4 is required for the maturation process of red cells in the bone marrow. You need a thyroid hormone for this to be completed. And certainly there is evidence of bone marrow suppression in underactive thyroid disease. Whilst in an overactive thyroid, we're even less clear, with authors talking about altered iron metabolism, problems with red cell lifespan, and not really giving a clear definition of why a hyperactive thyroid causes problems. And this is complicated even further in Graves' disease, where the inflammatory process of an autoimmune reaction is causing something analogous to the ferritin-based component of anemia of chronic disease. So, in short, a knackered thyroid knackers everything else. And if you look at enough lists of what causes microcytic, normocytic, or macrocytic anemias, you'll find thyroid disease in at least one in each list. What we do know is that in the majority of anemias related to thyroid disease is that they improve if you treat the underlying cause and sort out the thyroid problems. So if you're investigating anemia, and you got to the stage where you're doing hematinics, it's probably worth throwing in a set of TFTs as well. Cause 9. And it's no good you lot sitting there going, Jings, Crivens, help my bub, how long is this going to go on for? You only have to watch. I have to write this and draw it and look stuff up, and all you have to do is watch, so shut it. Anyway, it is nearly done, I promise. Cause 9 is pregnancy, and I don't know if you noticed, but I've been dropping hints on this already. Most things that cause anemia can be there in pregnancy, so increase in plasma volume, aplastic anemia, hereditary stuff, and hemolysis I've already mentioned. Pregnant women also have unexpected blood loss, and it's not unusual to get B12, folate, or iron deficiency when making a new person from scratch. So, though pregnancy is on the list, it really is a case of considering any of the above. Same goes for cause 10, which is alcohol and liver disease. Overuse of alcohol that causes occult GI bleeds and malabsorption of diet or dietary insufficiency of B12, folate, and iron. Additionally, the liver produces many of the proteins that manage iron storage and release. So again, liver disease and alcohol can cause pretty much all of the above. Cause 11 is mixtures of micro and macrocytic anemia. So if you have half the cells at 75 femtoliters and half at 125 femtoliters, the average cell size, or the MCV, will measure 100. So how do you spot the mixed disease? Well, you look at RDW, which is red cell distribution width. It's another bit of the full blood count no one looks at, but what it does is measure the width of loads of the cells and sees how much variation there is. So if all cells are roughly the same size, RDW is low. If you have a macrocytic or microcytic anemia, it will go up as the mixture of cell sizes varies, and you have a mixture of large, small, and normal cells. It's what's called anisocytosis, so not all cells are the same size. You'll see a change in the RDW. So normally you get a change in MCV to match microcytic or macrocytic anemia, but in a mixed disease you'll get a normal MCV but high RDW. Normal value is 11.5 to 15.4%, but don't remember this, just look at it on the form when you get your blood results back. One last one for RDW is thalassemia. You remember the one with the map? So in thalassemia, all the cells are small, so MCV is low, but RDW is normal. And that's it for types of anemia. All we've got to do now is check all the bits of the FBC, then there's a daft cartoon, and we're done. So, if we look at an FBC printout, haemoglobin we've done. I think we've probably covered MCV as much as any sane person would like. MCHC was the one that helped with hemolysis and odd cell shapes. Hematocrit, or HCT, as we showed, is a straight line when plotted against hemoglobin. RDW we did 54 seconds ago. So what's left? Well, RBC is the number of red cells in a litre, which in this example is 5 times 10 to the 12, or 5 trillion per litre. And I want to show you a wee thing to give you an idea of how many cells that is. So let's say we're going to count all the red cells in a person. We'll start at midnight on the 1st of January 2022 and say it's going to take a second to count each one, which seems a bit slow, but you've got to pick each one out with teeny tiny tweezers and put it in the counting pile. And if it's midnight on New Year, yeah, probably not concentrating that well, if I know any of you lot at all. So to count to 1,000 seconds, that takes us to 16 minutes and 40 seconds past midnight. To get to 1,000,000 is going to take us till 13:46, quarter to 2ish in the afternoon on the 11th of January. To get to 1,000,000,000, and that's 10 to 9, is going to take us till the 8th of August, 2053. Now, you've only got to do that another 1,000 times to get to 1,000,000,000, or 10 to 12, which means we should be done on the 1st of February in the year 33,270. Start at the edge of apostasy for you Warhammer geeks out there. But that's only 1 trillion, and our sample RBC was 5. So we've only got to do it 5 more times and we're there. So to count the full litre will take us until the year 160,462. But that's just 1 litre, and we decided people had 5 litres of blood to make the maths easier. And we count all the cells in the body, so we've promised, so let's do it. So that's multiply again by 5 times, so we get to 25 times 10 to the 12, which will take us until the 12th of March in the year 794,222, just after 7:15. So there's no point in going to bed after that, you might as well just stay up. Now, I don't know why I told you that, other than I found it fascinating, but it's just to give you an idea of just how many red cells we actually have, and it's lots. MCH is mean cell haemoglobin. So how much haemoglobin's in a cell, which is slightly different to MCHC, and this is a calculated value. How you calculate it is to divide the haemoglobin concentration by the number of red cells. So it's a relatively crude measure. But if you plot MCV against MCH, again, you get a pretty much straight line. Though some evidence suggests that MCH is slightly more sensitive at picking up anaemia and differentiate anaemia than MCV is. Now, the more observant of you have spotted that the MCH in the sample I've given is wrong. 140 divided by 5 is 28, not 29. So it's as if I just banged in a load of numbers when I was writing the slides and wasn't paying attention, or I planned it and thought I'll draw attention to a mistake I've made, or I'm just making it all up as I go along. Who knows? Anyway, that's all the bits to do with red cells, or red cell indices, if you want to give them their proper name. Now, I think depending on your standpoint, you might feel I've oversimplified this massively, which is fair, or overcomplicated this massively, which is also fair. To be honest, I know a lot more about red cell indices than I did when I started writing this. Some of the process I've described I'd either forgotten over time, or more likely not been paying attention when somebody taught me it. Some of the values, the red cell indices like RDW or MCHC, not values like brevity or weight, I didn't use much. And if you look at this Twitter poll, I'm not the only one. 63% of respondents, of which there were about 2,000, only use MCV. Now, after writing this, I'll probably be expanding my practice from being one of the 63% who only used MCV, though I can highly recommend this Twitter thread if you're interested in red cell indices. Though I'd probably leave it a week or two after watching this, otherwise you'll realise the massive amounts of plagiarism I've done. I'm going to finish with a short cartoon that I did one afternoon when I got bored in a meeting. And then it took me the whole afternoon. So we're going to pretend that it teaches us something important about how anemia can change over time. Imagine we've got a bloke. He's perfectly happy. He's got a normal haemoglobin. Initially, even though it's clear to the independent observer that he's losing blood, his haemoglobin will actually be normal because he hasn't started to hemodilute yet. As he starts to hemodilute, he may start to develop a normocytic anemia due to the reduction of red cells. But if he's lucky, he may develop a macrocytic anemia, but because even though he's losing red cells, his marrow will release reticulocytes to compensate for the blood loss. But if the bleeding continues long enough, he will become iron deficient and develop a microcytic anemia. And if it continues, well, one of the important things you have to learn is that one way or another, all bleeding stops eventually. And that's it. Thanks for watching. I hope it simplified some of the complexities of haemoglobin, or given you some ideas as to when you should be contacting haematology for help, or at the very least, entertain you for a bit. Ta-da!